So last time we talked about templates and how that was going to be used to generalize the way that we use our classes. So the idea with the example that we looked at was we had that stat class that we implemented, but we made it a templated class so that we could really create stack objects of any underlying type, such as an integer, character, double, or even perhaps the type of another class type, such as a string stack object. And we saw that you could apply that idea of templating at both the class level and the individual function level. So in the application program, we also saw a standalone function that was also templated. And we also have within the STL library several what are called container classes, which are also templated classes, but these are built-in classes. And when we think about some of these very general operations, like going through, for example, each element in the structure and maybe printing out, for example, all the contents, or inserting a new element somewhere within the structure. A lot of that can really be through the help of the container classes. A lot of those very common operations can be generalized through the various functions that are available in the underlying container classes. And so we'll look in particular at what are called the sequence containers. So these are container classes where we can, in effect, think of the elements as being a linear type of structure, where there's a clearly defined order from the first element in the structure to the very last element in the structure. And you certainly have talked about things before, like, for example, linked list or array, which is really just built off of the concept, or vector, which is built off the concept of a built-in array. And so in general, certainly there are different types of structures that we can work with, right? Because we know that the big difference between an array and a linked list is that the elements of a linked list are not stored together in memory. And certainly if you write out your own class or your own structure declaration, then the way that you process the elements of a linked list, for example, is going to be different than the way that you would process the elements of a vector. Because we know that since a vector is really just built on an underlying array, that we can just access things relative to the beginning of where that array starts in memory, using things like offset notation with either the brackets or the star, right, with pointer notation. And whereas you can't do that, right, with the linked list because they're not stored together in memory. But with container classes, it essentially generalizes this whole process, right, of doing these common operations like traversing the structure, potentially in either direction, meaning forward or backward direction, and also accessing an element or things like insertion, for example, and deletion. Because we also know, again, going back to differences between arrays or vectors and linked lists, that certainly there's different things involved, right? Between inserting, for example, into the middle of a vector versus inserting into the middle of a linked list structure, right? Because if you're going to insert into the middle of a vector, then there's going to be a shifting aspect to it, right? Where you have to move things around to make room for the new element at the vector, right? Whereas a linked list, you don't have to do that, right? Because it's not stored together in memory. So to insert a new element into the middle of a linked list, you just have to really move some pointers around. And also depending upon whether it's a single linked list or maybe a double linked list. So, when you're working with these things natively, of course, there's differences, right? There's differences in the logic and the way that you would write out the code for doing things like inserting into the middle, of a linked list, whether it's a linked list from a structure declaration or maybe a class declaration, versus, the code that you would write out to handle things like inserting to the middle of a dynamic array. But with a container class, a lot of those details are hidden, right? Because a lot of what we do in general in high level languages is we abstract what's really going on, right? And the container classes, to a degree, do that as well. Meaning that, as we'll see, that there's a lot of these common functions that can be used with the different objects of the different container classes. And it's really the same function regardless of which of these one of the classes you're using. So meaning on a conceptual level, we can think of it as, well, regardless of what type of structure I'm dealing with, I can push a new element to the end of the structure with really just calling the right function from the container class. And of course, behind the scenes for you, it's doing the actual real work based on what type of structure or what type of container class it is that you're actually working with. And so you're very familiar with vectors, but there are other container classes as well. And there's really 5 in particular that make up what we call the group of sequence containers. And like we talked about in chapter 18, these are also all templated classes, meaning that when you create the object, you also specify the type, right? Because whether it's a doubly linked list or whether it's a vector, we still want to be able to know what type of elements it's going to be stored. And so we'll look at really 5 different sequence containers, but they're really, in the end, based on one of 2 things, really, an array or a linked list, although we'll see the queue is a little bit interesting in how it's actually internally implemented. But they're really based on one of these 2 major implementations, right? Either an array-based implementation or a linked list implementation. But we do have actually a total of 5 of them. And 3 of them are based on an array. One of them is vector itself, which we know that that's really just an array that can grow or shrink on the fly, right? Meaning it can grow or shrink in size while the program is running, because it's really based on an array that was created with the new operator, for example. But what a vector is really good at in particular is dealing with things at the end of the structure. So these container classes all have their different various advantages and disadvantages. Certainly anything that's based on an array implementation, one of the advantages always is the fact that you have random access, right? Meaning we can go directly to any element in the structure without having to access the elements that come before it, for example, or perhaps after it to get to that element. But beyond that, because we'll eventually look at the differences between things like vector and DQ, but beyond that, the vector is really good at dealing with things like insertions or deletions at the end of the structure. Um, the idea being that when we talk about a vector, we know that it can change in size, but really we maintain both a size and a capacity, where the capacity would actually reflect the true amount of memory that is currently allocated for the array that the vector is based on. And size just means how much you're actually currently using. And the idea being that if you, for example, if your current size maybe is 10 and your capacity is 20, so meaning you've allocated a block, for example, in memory where you can store 20 integers back to back, but you only have 10 of them stored, and now you want to insert a new element to the end, well, that's just a matter of putting it there, right? We don't actually have to shift anything around, um, given the fact that we're inserting at the end. And if we haven't reached the capacity, then that's just a matter of putting the new element at the end. If we have reached capacity, then we still will have to go through the process of reallocating the array that the vector is based on somewhere else in memory with the larger size, right? And then copy all the original elements from the original array to the new array, and then put the new element at the end of that now larger array as well. But in general, vector can do pretty good if we're primarily only doing insertions and deletions at the end of the structure. It's a little bit more involved to do insertions and deletions at things like the front or the middle, which is also why we have these other sequence containers. Actually, yeah, I decided to cancel quiz 13, but we will still have discussion board 13. So this week you'll have your extra credit assignment, and then the last discussion board, or discussion board 13. But no quiz 13. So what we're going to ultimately see is that when you use these container classes, it really sort of generalizes the whole process because you're going to be using the same kind of function calls regardless of which container class you're actually using. But we do still want to keep in mind what's really happening behind the scenes. So if we use the vector container class, then we know the underlying implementation is really an array, and we want to take into account, the limitations in terms of performance with an array. So an array really is never going to be the best option, right? If you're doing things like, for example, a lot of insertions or deletions in the middle of the structure, because that leads to the situation where you can't avoid having to move a bunch of things around. And also in the case of vector inserting at the front, also same issue, you have to move things around. So vectors are really, really good if we do need that random access. And at the same time, maybe we're only or primarily doing things at the end, right? So we're not doing, for example, a lot of insertions or deletions at the middle or the front, but that's primarily happening at the end. And we really, do want, for example, that random access. Well, then vectors are a really great choice in that case because it's kind of giving us everything that we really need. But in terms of which one you use, you want to think about what kind of operations are going to be commonly performed. So again, vector is not really a good choice if you're doing a bunch of insertions or deletions somewhere other than the end, right? Such as the front or somewhere in the middle of the structure. The extra credits would be, yes, the 14th assignment. So there's 13 regular 13 regular assignments, and then the extra credit one this week will yes, would be the 14th. Mhm. And so if we're inserting at the end, really one of two things is going to happen depending upon whether we're actually at the capacity. So with both vector, and then as we'll see also with things like DQ, we do have separate functions for both size and capacity. So assuming this is our initial state of this vector, which we're just saying in this case starts, we're assuming it stores integer numbers, which are 4 bytes each, and it starts at address 20. And so initially it has the elements 1, 2, 3, 4, and 5. Now, we certainly know that if you want to insert anywhere other than the end, right, you're going to have to shift one or more of the other elements to make room for it, which is why we'll look at some of these other sequence containers, which are going to be better if we're doing a lot of those type of operations. But when we think about inserting at the end, either the best case actually is if the size is still less than the capacity, because then we could just simply come down here, right, and put the 6th element there. If we already have reached capacity, meaning that this array physically was declared to, of that size to store 5 integers, then we would still have to redeclare the array of a larger size somewhere else in memory, copy these 5 elements over, and then at the end, put the new 6th element at the end of that block. So it's going to be one of those two things that happens here. But that's why we, commonly with the vector class, we try to reduce the number of times that we have to go through that whole process of reallocating the block with a larger size. And so, there's different ways to potentially approach that. One might be to, for example, double the capacity whenever you reach it. So that's going to give you that extra, wiggle room, so to speak, before you have to start doing the process again. Of course, it's also going to take up more memory if you do that, as opposed to just increasing the capacity by 1. But especially if, we're mainly focused on things like CPU time, then that would be one possible approach, would be things like doubling the capacity. And then that's going to reduce the number of times overall that we have to go through this whole process of adding in a new element. So we'll just, for here, we'll assume that that maybe size, for example, meaning what we're currently storing, the number of numbers that we're currently storing is 5, and then maybe capacity, for example, is 10, meaning that we can store up to 10 integers before we would have to dynamically recreate the array somewhere else in memory. So that would be the best case here. So then we're just going to simply at the next sequential address here, meaning in this case, address 40, we would just put the value 6, and that would be the end of it. And then the worst case would be is, if we have hit capacity, then we're just going to declare a whole new block somewhere else in memory, and then we're just going to go through that whole process of copying from the old block to the new block and then deleting the old block. But we still, at least even then, didn't have to worry about shifting things around, right? It was just a matter of copying, right, from the old block or the old array in memory to the new array. So that's why vectors, and that's also why in terms of the vector class, right, we have things like a push, push back and pop back, but not the corresponding front functions. Of course, vector does have functions like insert, which can ultimately be used to insert anywhere, but again, it's not really in general good performance, right, to insert a new element at the front or the middle of a vector, right? There's other choices that are available that can handle that in a more optimal way compared to vector. So you do want to think about what type of operations are going to be common, and because that should have an impact on which of these container classes that you would use, right? You kind of have to weigh the different operations and take into account, how they compare across the different sequence containers. And because certainly, in certain applications, some operations might be more common than others, right? So if we're doing something where there's really not a need in general to insert somewhere other than the end, then in many cases vector is going to be good enough, right? We don't have to necessarily use something else. Especially again, if random access is needed. So that's another thing that you have to also take into account as well, is it really important that you be able to directly access anything in the underlying structure without having to access other elements first, right? Which is what we call random access. Um, because if that's the case, then there's a few that we can choose from, but it would rule out things like a list-based implementation where you can't just go randomly to any node. So we have to weigh those kind of things as well. But that just gives you an idea of how things like the vector class works. So that would be really the best case scenario for inserting a new element to the end of the vector, and then the um, worst case is where you have to reallocate it. But again, at least we're still not having to um, actually shift elements around in order to make room for the new element. We're just simply, in that case, copying it from one location in memory to the other. So that'd be the alternative situation here with a insertion at the end. So meaning, for example, if maybe this time capacity was initially 5 and size was also 5. Then what we might do is, because we actually reached capacity and we wanted to now insert a 6th element, now we might actually double it from here from 5 to 10, and then we're just going to copy the elements from the old to the new array, and then when that's done, we can go back and delete the old array, so that way we don't leave it there. Now it just means that now our vector in general, right, is going to be somewhere else, because the whole idea would be, if we've actually reached capacity, we can't just simply go to the next sequential address, meaning, for example, address 40, because that was not part of the original block of memory that was allocated for the array. So it would not in general be safe to just overwrite that. But what we can do is just declare a whole new array of the larger size, actually size 10. So we're not actually using here, we're not necessarily going to be using all of the newly created array, but we're going to create an array of that size. And then in general, of course, it's going to be somewhere else in memory as far as where that actually is declared. So then the end result of all this is that the old array, which was previously at address 20, is now going to be gone. And now we're going to be working off of um, this new larger array, which now would have, for example, size 6. And assuming we followed a doubling type algorithm, then capacity would also be 10 here. So we'd be able to insert 4 more elements from this point before we'd have to go through the process again, right, of reallocating it a second time with a larger size. And so that's the basic idea of vectors. So really, it's actually really good for those operations at the end. Not really so great anywhere else in terms of insertions or deletions. Um, Now, but when you do think about those things like for example the middle of the structure, um, that's also why we have a list, right? The idea of a list, which unlike an array is not a contiguous structure. Right, because the whole reason why we have to think about shifting with an array is because we have this limitation or this constraint that says that all the elements of the array have to be stored together in memory. But with a list-based implementation, we don't have that constraint, right? Because with a linked list type of setup, instead of relying on the fact that the nodes are stored together in memory, we instead work off of pointers to get from one node to the other node. And because of that, when you think about things like insertion or deletion, there's really no shifting aspect, right? Everything just comes down to simply updating the pointers in the correct way. And because we know that in general with the linked list, whether it's a single or a double linked list, we're certainly going to have a head pointer to the, right, if we're implementing this ourselves, then we're going to definitely have at least at a minimum a head pointer to the first node. We, even with a single linked list, might choose to also have a tail pointer to the last node. And then we're going to form the individual links between all the different nodes to make a true list. But because of the way that that works, insertion now is a much more simplified process because I don't ever have to worry about shifting. If I have 1,000 elements in my linked list and I want to insert in the middle, that's fine, right? I just have to end up at the right place. So there's some traversing that's involved because it's, again, not a random access structure. But when I eventually get to the right spot within the list, all I have to do at that point is really just, update some pointers. And now I've simulated the idea of inserting the node into the right spot within the middle of the list. So, a list is really good for especially those things like insertions or deletions at the middle of the structure. And also compared to vector, they're inserting at the front, right, is also going to be in general better performance with a list than a vector, although we'll eventually look at DQ, which can actually be even better yet for insertions at the front especially. But so that's why we also do have those list type structures. And just in the same sense that we, if we were doing this ourselves, we could implement the linked list in terms of either a single linked list or a double linked list. There's two separate container classes for both as well, with actually the single linked list being a newer one as of C++11. But both are possible. But we know that in general, when we think about a linked list, just do a quick conceptual example here, but you looked at this a lot in 165, but we know that in terms of the pointers, you have things like your next, at least your next pointer anyways, if it's single, and that the type of that, right, is the same type as the class or the structure itself. And then you have whatever actual values you want to sort in the object. So for example, maybe here we're just storing a bunch of numbers in each node, but we certainly could have other things there. And of course, we may have several functions as well, like insertion, append, delete, destroy, and so on and so forth. But we know that fundamentally that when we think about linked list, that again, that it's a very different layout, certainly compared to array, because it's not contiguous. And here, we'll assume this is just for a single linked list for now. And then in this case, we're just assuming that maybe just numbers are stored in each node or each object. And then in addition to that, certainly it's going to have that next pointer. In addition to the next pointer, which every node has, we also maintain things like a head pointer, right? And the head pointer is not part of the structure, or in this case, the class, because that's not something we want to store for each node, right? But rather there's just one head pointer, which either points at null pointer if the list is empty, or it points at whatever the first node in the list is. So we have things like head, and then we have those next pointers, right, coming out of each node. And then what we can do with the last node, right, is just have its next pointer point at null pointer, because that's why with the linked list, we commonly will check for null pointer as far as knowing when to stop, right, when we've reached the end of the list and when we can stop looping. Now, what we're doing here is related to the sequence container that's called forward_list, meaning when you use that sequence container, the underlying structure that it's based on, right, is similar to this, a single linked list where the links only go in one direction, but not the other direction. And we usually call this one here next. Right, and then we have something like that, right? Just in this case, just a few nodes. And we may have also a tail pointer to the end, right, as well, especially if we're going to do things like maybe append type operations. But it's certainly at a minimum, we're going to have a head pointer to the beginning, right? And so again, each of these pointers coming out, we know is called next. But when you think now about the same types of operations, meaning things like insertion or, for example, deletion, well, this is a very different setup, right, compared to an array-based setup, because now we're talking about lists with pointers. And so, for example, if I want to insert a new element between node 2 and node 3, well, all I have to really do is, through the help of pointers, get to the right spot and then just go ahead and update those pointers, right, to simulate the idea of inserting this node in between node 2 and node 3. So in particular, and again, we're just looking at this on more of a conceptual level to give you an idea of, what's actually happening when you use the container class, right? Because again, the container class is an alternative to doing all of this yourself, right, with your own linked list type class and your own insertion algorithms and so forth. But so here, we could have a general looping type algorithm where, so in addition to head, we'll need some sort of other pointer to help us with looping. That's going to get us to the right spot within the list. And then assuming we're able to end that loop with the pointer in the right spot, then we can use that to just update our pointers and insert that new node in between, in this case, node 2 and node 3. So in terms of the usage of the container classes, right, it would just be a matter of calling the function, right? That's kind of the whole idea, is it's sort of abstracting, a lot of these details away and doing the underlying work for you. So we'll see that, for example, with if we're using the forward list class, you have a function called push front, for example, which inserts a new element to the front. But in terms of what's really happening, right, is we're working off of pointers to physically actually do the insertion, or similar idea with deletion. So here, of course, if we're using a list type implementation, then we don't have the benefit of random access, right? Because it's a trade-off, just like most things. Because it's not stored in memory, which is what would be needed for it to be random access. So we don't have the benefit of random access, but at the same time, since it's not stored in memory, we don't have that whole constraint that arrays have, where shifting has to happen when you're inserting somewhere, for example, in the middle of the structure. So again, especially if we're doing a lot of insertions and deletions in the middle of the structure, then a list is going to be better for us, because we really just have to update those pointers. And we'll assume here that we have a separate pointer to the new node, which is not currently in the list, but we're about to put it in the list, right? So we certainly need to have a pointer to that node. And then, again, when you think about the general idea of a basic traversal algorithm, you're going to have some sort of looping type pointer. And in fact, we'll talk about the idea of iterators when we look at the actual container classes. And we'll see that iterators are really ultimately based on arrays. But we'll see how they're used with your container class objects. But so the whole idea is we need to iterate through this list, but depending upon where exactly we want to do the physical insertion. So, and we can, in general, we'd also have to handle things like, for example, updating the head pointer if you inserted to the beginning of the list, and so on and so forth. But in the beginning here, we would start with this pointer, for example, at the head node, and then we would have a looping algorithm, right, where in general PTR would be able to move right up throughout the various nodes in the list. And so the whole idea in this case is that we would want to have PTR and end at the right spot in the list at the time the loop is over with. And so in particular, if we did something like, so here we're talking about inserting between node 2 and node 3, so somewhere in the middle of the list. If, for example, PTR, let's say the loop ends and PTR is pointing at node 2. And again, the goal would be for this node 5 here to be in between node 2 and node 3. So meaning that node 5 is now going to be the new third node in the list coming after node 2. But if we end the loop in such a way that PTR is pointing at node 2, well, now we're going to be able to form all of those links, right? Because, for example, we can, there's really 2 links that have to be changed here, right? But we can take the, for the new node here, we want to ultimately have its next pointer point at node 3. But we can do that through working off of PTR. So in general, of course, we could have a much larger list, and we may have to go much deeper into the list depending upon where we want to insert. But the general idea here in this case is that PTR is pointing at the node before the position where we want to insert the new node. So again, PTR is just pointing at the position before the node, position where the new node is actually going to be inserted. So now, we can say things like, for example, new node arrow next, meaning the next pointer that comes out of the new node, equals PTR arrow next. Because that's going to be one of the two major things that needs to happen here as far as connecting this new node, which is 5, to the node number 3 there, is something like new node arrow next equals PTR arrow next, right? Meaning take new node's next pointer, right, and make it point at what PTR's next pointer is pointing at, and PTR's next pointer is pointing at node 3. We can do that first, right? So use PTR itself to help refer to node 3, and then just make PTR arrow next, right, point at new node to update that link. And then that's going to simulate the idea of inserting this node at the middle of the list then. And that's it, right? So when the looping is done, that is, those are the two major statements that have to happen. The new node arrow next equals PTR arrow next, and PTR arrow next equals new node. So now when we talk about, the next pointer coming out of here, right, it's going to be going now to node 3. And then now we want to change this one to go there. And that's all we have to do, right, to insert into the middle of this list structure. And it's also a similar idea with deletion, right? With deletion, same idea. You're gonna, first of all, you're gonna physically, assuming everything was dynamically allocated, as it often is with a list type structure, you're gonna make sure that you also release the memory, right, that was taken up by the node, but then you're gonna update the pointers as well. So with both types of lists, right, meaning a single linked list and a double linked list, when we talk about things like insertion or deletion, we really just have to make sure that we update the pointers. And of course, in the case of deletion, that we want to also make sure that we release that memory as well. But that's the basic idea here. So that's why a list is able to do so much better than something like a vector when you're doing these type of operations in the middle of the structure. So this here is a single linked list, which would correspond to the container class that's named forward underscore list. And then we also have the container class list, which is actually the original one that came first, but that one corresponds to a double linked list, right? Where you have the links going now in both directions. So in terms of the class setup, the doubly linked list, right? We need to have that second pointer. So it takes up, also more memory compared to a single linked list, since you have to store 2 pointers for each node. but you have that flexibility also of it now being bi-directional, right? And in the sense of being able to go in both directions, whereas you can't traverse in both directions with a single linked list. But with a doubly linked list, you have both pointers, and but same idea. It's going to also be, more efficient than something like a vector with those operations, especially at the middle of the structure. But now you also have the benefit as well of bidirectional. So not only can you go from front to back in terms of traversal, but you can also go from the back to the front. So each node is going to have a previous pointer. So actually node 3 is now going to here. And then in this case, we do certainly here want to maintain, right, in general, a tail pointer as well. So meaning at this last node 4 here, we'll have tail. And then as far as the first node's previous, right, that also is going to point at null pointer. So the first node's previous and the last node's next, right, they can both point at null pointer. And now you have a true bidirectional structure. So you could, for example, right, if you were doing this yourself and you were doing things like a traversal algorithm, you could start your, right, for example, your iterating pointer like PTR, start by, for example, pointing that at what the tail pointer is pointing at, and then follow the previous pointers until you reach null pointer to traverse, right, the structure in reverse order. Because you could start here, follow the previous pointer to get to node 3, then follow the previous pointer to get to 5, and then follow to get to 2, and then to 1, and then eventually to null pointer over here. So that's what we mean by bidirectional. Now, and we'll eventually see that you really have a hierarchy of these different types, right? Because, for example, when you think about a vector, well, a vector is random access, but it's also can go certainly in both forward order and backward order, which is why you actually have the most flexibility in that sense with a vector. But at the same time, we know that because of the underlying memory structure, that things like insertions and deletions at the middle or the front are not really efficient, whereas they can be done efficiently with things like a list-based implementation here. So here we have just the basic idea of a now a double linked list, but similar idea here. Also, things like insertions and deletions are really just going to be a matter of updating the right pointers. Because, for example, like at this point, if we wanted to delete one of these nodes, like maybe even delete node number 3, for example, which is now the 4th node in the list. Well, in terms of what really needs to happen, right, is you would just need to make sure that you're connecting node 5 and node 4, right, those 2 nodes together, and then just physically delete node 3 with the delete operator. So, I mean, you could, for example, have a pointer, a pointer pointing at node 3, and then you'd have to rearrange the links between node 5 and node 4, of course, to make those 2 nodes be directly connected to each other. And then just at the end of all that, just use the delete operator over your pointer that's pointing at node 3. And so in that same sense, single compared to the singly linked list, it still does not involve having to shift any elements around, right? So in both cases, with both the single or the double linked list, it's just really a matter of updating the pointers as far as how we actually go about inserting or deleting in the middle of the structure. So we don't have that overhead. That we do with things like a array or vector-based implementation. So that gives us an idea now as far as why we have these different container classes. Again, there's really 5 of them, but at the end, really, they're based on one of 2 things, either an array-based implementation or a list-based implementation. with a few different variations, such as single versus double linked list. And then DQ, which is actually kind of interesting because it's still a random access structure, but it's really a semi-contiguous structure where some of the elements are stored together in memory, but the whole entire DQ itself as one entity is not all stored together in memory. But now in terms of the container classes, right? So the container classes are an alternative to doing all this yourself, right? Meaning that, of course, anything that you could do with a container class, you could do yourself, right? Just in the same sense that instead of using a vector object, you could just, use your own dynamically managed array and do everything that way, right? Working off of pointers and, using operator new and delete and so forth. But the idea is that we do have these built-in container classes in the standard library that correspond to these major ideas, like a dynamic array, which is the whole idea behind a vector, or a linked list, either single or double, which corresponds to those two container classes. And so the 5 sequence containers that we have are array, vector, DQ, list, and forward list, meaning the 5 built in, right? So these are built-in templated classes in C++'s standard library. And we call these sequence containers because regardless of which one we're using, and regardless of how it's physically stored in memory, when we think about it on a conceptual level, right, we think of the elements as being in order, in a certain order. So even with the linked list, right, which is not stored together in memory, we still nonetheless think of, this is, for example, the head node. This is the second node. This is the third node. This is the fourth node. This is the fifth node where my tail pointer is pointing at. So even then, right, conceptually, we still think of this as an ordered or a linear type structure from first node to last node in the same way that we conceptually think about an array. So that's why we use that term also sequence container. So because we think of it as a linear type structure where the elements are lined up in a row, basically, right, horizontally. Now, we do have array. And when we say array, we're not talking about built-in array. We're talking about an actual templated class, right, called array. But the idea is that unlike things like vector, it cannot grow or shrink after it was initially declared. So the others are all dynamic, what you might call a dynamic structure, meaning vector, DQ, list, and forward list. All of those certainly can change at any time, but array is the one that can't change. So in that sense, right, it has perhaps more limited usage, but you can use it if you're working with a static size structure that where you're going to declare it one time and then you're never going to need to change it for any reason. So you've got array, you've got, of course, vector, of course, dynamic, right, based on dynamic array. You have DQ, which is kind of an interesting one, which we'll look at the details of that a little bit more later, but it is random access like vector, and it can also grow and shrink like a vector, but the elements are not all stored together in memory. So array, vector, and DQ, because we'll eventually talk about the categories here, those are all random access, right? The highest, we'll eventually talk about things like iterators, and that's the highest level because you can go forwards, you can go backwards, and you can also go randomly to any specific location without going to the elements before it. So we call that a random access iterator, which is the highest level because you have the most flexibility, right, in terms of what you can do. The next lowest level iterator is called bidirectional, meaning you can go in both directions, but you can't go randomly to any random location, and that would correspond to a doubly linked list. So the container class itself is just the word list, but it corresponds to a doubly linked list, which is a bidirectional type of iterator, as we'll see. Bidirectional type of structure, and then in terms of the hierarchy here, the lowest one would actually be what's called forward underscore list, which corresponds to a single linked list, because we call that one just a forward iterator. So it can't randomly access any element, and it also can't, it's not bidirectional because you can't go from the back end towards the front end. You can only go from the front end towards the back end. So among the three levels in the hierarchy, that would be the lowest level of iterator. That one, again, is called forward underscore list, which is based on a singly list. Or the lowest level of the three iterator types. Now, we've kind of talked a little bit, and a lot of this might have been review, for example, from 165, but again, we always want to keep in mind how things really work, right? So that's why we talked about these things a little bit here. But in terms of the container classes, the whole idea is to generalize a lot of this stuff, like adding a new element or removing an element, and so on and so forth. And so we'll see in the code example that the good thing about all this is that even though we know that fundamentally, the implementation, the actual true implementation of a double linked list is very different looking than the implementation of a vector, but in terms of how you actually use the container classes, it's very similar, right, in terms of the function calls and how we use the iterators. And so when we talk about an iterator, right, that's what we use when we talk about working with these built-in container classes. But basically, it's like a pointer. So in the same sense, right, that when you think about a linked list, you think about, a pointer like PTR here, which we use to iterate through the list. Because if you're implementing a linked list yourself, you do a lot of things like PTR equals head, right? And then PTR equals PTR arrow next to move it up one time, and then again, and then again. Or if you're traversing backwards, make PTR initially point at tail, then say PTR equals PTR arrow previous to move it back, move it back, move it back, right? So you're directly working with a pointer that you've declared yourself, right? So you can imagine here, if we implemented this doubly list class ourselves, and then did all the common functions like traversal, traverse from front, traverse from back, that's what we would be doing, right? We'd be declaring our own pointers of, in this case, doubly list star, assuming that's the name we give the class here. And then we would use those pointers directly, right? Well, the same thing, of course, has to happen ultimately if you're using a container class, but we're abstracting really a lot of the details away in doing so. So we have what are called iterators that are used to, in a general sense, iterate through whatever type of container class it is that we're working with. The whole goal of all this is to not get down to the details of the actual differences of working with the linked list versus an array, to just sort of think of it as all the same, right? Because regardless of which of the five I'm working with, conceptually at least, they're all linear type structures where we think of the elements as being lined up in order. And that's the whole idea, right? Is to, on some level, simplify this whole process of actually doing things with the structure that we're working with. And so that leads us into what are called iterators. But really, an iterator is just like a pointer. But we'll see that there's functions that we can use to help us with iterating through these various container classes. So we have different types of iterators and also different functions that we can use to ultimately iterate through the structure in the correct way. And it actually turns out, because with many of these, right, we can in general iterate in both directions, both the forward direction and what you might call the reverse direction, right? But meaning from the back end towards the front end for whichever structure you're working with, except for forward list, right? Because forward list does not have the capability, since it's based off a single linked list, does not have the capability of going in reverse order from the back towards the front. But the other four do, right? So array, array, vector, DQ, and list, which is doubly linked list, can all do that. And so what that leads to actually are really four different types of iterators, because there's also the issue of const as well. Because the iterator is like a pointer, right? Where if you think about the structure, regardless of which class you're using, you're going to be iterating through, right? Which is why we call it iterator, but you're going to be iterating through the structure using this iterator. Meaning at a certain point in time, it's going to be pointing at the first element. Assuming we go, for example, in forward order, then we would start it with, pointing at the first element. Then it's going to point at the second element. Then it's going to point at the third, and so off. And eventually, it's going to get up to the last element if we need to go that far. And likewise, if we're going in the reverse direction, then we want to do things like start at the last element and then move to the left, right? If you think of it from right to left or left to right, then last element would be the rightmost element in our linear structure, and then move to the left, right, backwards, 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 backwards in reverse order. So we do need to have different types of iterators to support all that, because you have on the one hand iterators that are designed to work when you're iterating in the forward direction, and then you have iterators that can be used when you're going in the backwards direction. And then there's also the issue of const as well, meaning that if the iterator type that you're using is const, then that iterator cannot be used to change any of the values in the structure, right, that you're working off of, that you're iterating through. So I mean, the iterator itself can still be changed to make it point at a new element in the structure, but whatever it is pointing at, right, it's not going to be able to change that if the iterator is const. Just in the same way that you might use a pointer where the data part, right, of the pointer is constant, and then that pointer cannot be used to change whatever it's pointing at, right? So if you have a pointer to a constant data, and then you're looping through your array, for example, well, then you could do things like print out the contents of the array using the pointer, but not use the pointer to change the contents of the array. Similar idea with the iterator in terms of const. So really what it means is that we have these different combinations of iterators, depending upon if it's a forward iterator or a reverse iterator, and then also whether it's a const or a non-const iterator. Well, actually, iterator can return really either non-constant or constant, depending upon what type of structure we're working with. But the idea of iterator is that it's the one that you would use in general if it should be possible for the iterator itself to be able to change the contents um, of the structure that it's iterating through. So we have iterator. We also have what's called const underscore, right, iterator, which is similar idea, but the iterator itself is treated as constant, so it can't be used to change the objects. So in this case, it's definitely going to be a constant iterator. So it's not right. It's not going to be able to change it, but it still goes right. Still goes in the forward direction, similar to the first one, which was just called iterator. So we're not going to be able to use it to change the contents, but we can still have read access, right? And then it can go in the forward order. And then we have two for going in the reverse direction. Which are called reverse iterator and then const reverse iterator. So just the four combinations of, non-constant or const and then reverse or forward. So, but again, both iterator and const iterator, those are for going in the forward direction. So meaning we could use those with any type of structure that supports that. And really all five support that, because with all five of these container classes, we can certainly iterate in the forward direction. Because here we're talking about iterating, right? We're not talking about things like whether they all have, for example, a function called push friend, because we know that, for example, the vector class does not have functions like push front or pop front, and array doesn't have any of those functions, right? Because you can't change an array after the size has been set when it was declared. But as far as just iterating, right, we can always certainly iterate through any of these in the forward order direction. But for going in the reverse direction, we actually have a separate type for going in the reverse direction. And so we have reverse iterator and then const reverse iterator. So reverse iterator. And again, so if we don't have const there, then in general, if the iterator is pointing at a non-constant object, right, then it can in general be used to still change that object's contents, but it's used to iterate in the reverse direction instead of the forward direction. And then const reverse iterator would be the 4th one here. And so those are the four major types, again, four types of iterators here, just depending upon whether you're going in the forward or the reverse direction and whether it's constant or not constant. But so these four iterator types also correspond to actually 8 different functions, because we have combinations like for forward order or reverse order, and then constant and non-constant as well. So really 8 different functions. Because ultimately the whole idea with simplifying this process is we think about common operations, right? Which a very common operation is go through everything, right? Go through every node in the structure and do things like print it out, for example. And so we need to have functions in general that can refer to both ends of the structure, right? Like a begin type function and an end type function. But we have the different combinations because of things like constant and reverse as well. But the idea, and so we'll look at the functions that coincide with these 4 iterator types. So the function begin. So again, these functions are going to be combined with the iterators, right? So the iterator itself is like a pointer, um, but just like any other type of pointer, we have to think about, well, how are we going to, for example, initialize the iterator? And how are we going to stop iterating at the right time, right? That's exactly what these functions are designed for, to help us with initializing the iterator in the correct way, or also stopping at the right time. So, the begin function can be used to, basically what it does is it refers to the first element in the structure. So this is something that could be used with when we're going in the forward, right, iterating in the forward direction. So it can be used, for example, with this type of iterator, right? The first one here, but it refers to the first element. Now, end, we have a function called end as well. Now, it refers to not the last element in the structure, but one past the last element. So one past, right? One past the last element in the structure. And it's also designed for when we're iterating in the forward direction. So this is something that we can check. So it refers to one past the last element in the structure, and then it also corresponds to this to this first iterator type here, meaning non-constant and for the forward direction. So the whole idea is that in terms of the loop itself, since end is actually one past, right? One past the last element. We can set it up in terms of a inequality type comparison, um, meaning that the loop would keep going until your looping iterator is equal to the value returned by calling the end function. Because the way that the function actually internally works, right, is it's past the end of the structure. And when your looping iterator has reached that point, it's going to become right equal to that. So that's how we can, in general, stop the loop at the right time. So this is going to be one past or one after, right, the last element in the structure. So we're talking still about going in the forward order. So one past or one after the last element in the structure. Now, we do have constant versions of both of those as well, which are called C begin and C end. Same idea, except the iterator that it returns is guaranteed to be a constant iterator as opposed to iterator. So we have C begin and then C end. But again, it's going to return a const iterator. And then, so the name of the function here is just C at the beginning. And then same thing with C end. And just returns a constant iterator. Now that's the first four, right? So begin and C begin, C end. But we have a total of 8, right? Because each of these 4 also has a corresponding reverse version of it, meaning reverse begin, reverse end, because the full names of the functions are really begin and const begin, const end, and then reverse begin, reverse end, const reverse begin, const reverse end. So just all the, the 8 possible combinations there of constant and reverse and forward order. So the idea with R begin or reverse begin, so again, these 4, the first 4 are all for going in the forward order. So those 4 are all for forward order, and then the next 4 are all for reverse order. So the R means reverse, C means constant. But so R begin it's going to be going in the reverse direction, but it refers to, now we still use the word begin, but you want to think of it as you're going in reverse, right? So relative to that, right, you're beginning at the last node in the structure, or the rightmost node. You want to think of it as a linear type structure. So it refers to the last element, right? The last element in the structure. Which is the first one that you would visit if you're going in the reverse direction. And then it's going to return a reverse iterator instead of a just regular iterator type. Now, Rn, or reverse end. Well, we said that when you were going in the forward order, the idea was that, so begin would refer to the first element or the leftmost element, and end, and likewise cend, right, would refer to one past the last element. Well, it's actually a very similar idea when you're going in the reverse direction. So our end is going to be one before the first element in the structure. So the end functions never refer to an actual node, right? They're always one past or one before. So whereas end and cend refer to one after the last node, our end and cr end both refer to one before the first node, right? Because the first node is the last node that you would visit if you're going in the reverse direction, if you're traversing in the reverse direction. So that's how the R end and by extension also CR end work. So that's the idea of R end. And then you see our end is very similar, except constant, right? It's going to return a const reverse iterator. And that'd be your CR end. Then your also have CR begin. So that's why we have 8, right? 8 of these different versions of these begin and end functions because of the different combinations, different combinations of constant reverse and versus forward order. So 8 combinations here, but that's the idea. So a lot of these, some of these are similar to the others, but basically you have to think of it along those lines, right? When you're going in the forward direction, you want begin to refer to the first element, but you really want end to be one past the last element. So that way you can do an inequality, type comparison to stop the loop. Somewhat similar to how, when you're doing a linked list yourself, you might check for null pointer with your pointer as the stopping condition. So you always go one past the last node to actually stop if you're traversing the entire structure. But you want that concept to work regardless of which direction you're iterating in. So that's the very important thing here, is there's not really any key difference, right? Whether you're going in the forward order or the reverse order, you want it to work the same general way. So that's why R begin is still talking about the last element in the structure, the rightmost node, because that's where you would begin in the reverse direction. At the same time, though, you don't want to stop at the first node when you're going from right to left, right? You want to go one past it, right? Or in this case, the position that's one before the first node. And that's exactly what the R end or reverse end function does. So in both directions, you're going one past or one before, the last node that you're going to actually visit in the structure itself. Because you can check for that with an inequality similar to things like, while PTR not equal to null pointer type loop to stop a list that you've done yourself. So those are the functions that can be used here. So now at this point, we've seen 4 different types of iterators: iterator, const iterator, reverse iterator, const reverse iterator, and then the 8 corresponding functions, right, that coincide, right, with those iterator types, which were begin, begin, end, right? C begin, C end, R begin, CR begin, R end, and CR end, which covers all the different combinations um, that arise here. And so what we'll start to see now is that things like traversing the structure from, for example, forward order. Well, the code really is going to be the same, right? Regardless of which type of container class that you use. Because, if you want to do something like print out all the elements of your structure. So we could, for example, have a vector of integers, or we could just as well have a list of integers. But it's all the same, right, in the end, because all you would have to do is start by having your iterator, your looping iterator, right, point at the value returned by the begin function, which is going to be the first element in the structure, regardless of which structure type it is. And then that loop is going to keep going until you detect, right? Because you're comparing the iterator against the value returned by one of the end functions, right? So for example, if we're going in the forward order and then maybe we want to use the const versions because we don't want the iterator to be usable to actually change, the contents of the structure as we're going along, then we might use then C begin and C end, right? Meaning initialize the iterator itself with the value returned by C begin. And then in the second part of the for loop, compare the current value of the iterator against the value returned by C end. Because we said that C end was one after the last element. So it follows that until you've reached that point, when the iterator is actually pointing at an actual element in the vector or the list or the forward list or whatever, then the address in the iterator is not going to be equal to the address that's returned by the end function. So the loop is going to keep going and keep going and keep going. But eventually, after you've processed that last element in your underlying structure, well, at that point, you're going to increment one more time, right? And then the address in your looping iterator is going to become equal to the address returned by the end function. So you're just going to stop them. So when you think about, the three parts of the for loop header, you just need to initialize the iterator. You need to have the right condition where you compare against the end function. And then you need to use something like plus plus, right, to actually increment the iterator. And then, of course, in the body, you can have, the cout statement to actually print out by dereferencing. So we'll see that, when you're working off of an iterator like this, we still use the star operator to dereference the iterator, right? Similar to how you would use the star operator to dereference just a regular pointer variable that, of type int star, for example, that you defined yourself. And then that's all you have to do, right? Again, the code is going to look the same, though, regardless of which one it is. So that's kind of the whole point of these container classes, is it sort of generalizes all of these major types of operations across the different container classes. So we'll look at a code example where we're going to have different functions for, printing out the contents of a list, for example, or the contents of a vector, but the code is basically the same, right, in terms of what actually happens. And we'll even see that in terms of moving up the iterator, because here we talked a lot about the functions that are used to help initialize the iterator and to check the condition to stop it at the right time. But as far as actually updating the iterator, that's also simplified now. Because we're familiar with things like plus plus and minus minus, right? For example, so from 165 that if you have a pointer to an array or a vector object, that if you do ptr plus plus, right, that moves the pointer up one position. So now it's pointing at the second element instead of the first element. in the array or vector. Or if you do PTR minus minus, for example, it's now going to move backwards one position. Well, we have to think about the same kind of things, of course, with our container classes. And then, of course, with linked list, it's different altogether, right? Because with the linked list, if we're doing it ourselves, we can't just say PTR plus plus because the nodes of the linked list are not stored together in memory, which is why you see things like PTR equals PTR arrow next or PTR equals PTR arrow previous. But the goal here is generalization. So even here, regardless of what type of container class we're using, and really regardless of whether we're going in the forward or the reverse direction, we're going to just simply be using plus plus to move the iterator up, right, in the right way in the underlying structure. So even if we're iterating in the reverse direction with functions like rbegin and rend, we still use operator plus plus, right, to move from the tail end towards the head end in the left direction. Likewise, if we're iterating in the forward direction using functions like begin and end, we also there use operator plus plus to go from left to right, moving the iterator up. And again, it works with both list and forward list, vector, and DQ. Now, of course, behind the scenes, right, plus plus has a different meaning or a different underlying logic with the list versus a vector, because a vector is a contiguous structure, a list is not a contiguous structure. So, of course, there's more work happening behind the scenes, but in terms of usage, it's just plus plus, right? So we can use that with all of these container classes, and again we even use it in both directions. So meaning when you initialize a pointer with the rbegin function, meaning the reverse begin function, you use plus plus, not minus minus, to get one position over to the left, right? So if you're at the end, if you're at the last element through rbegin, and then you do plus plus, you're going to move to the left, right? And then if you do it again, you're going to move, and you're going to move, and you're eventually going to get to the front of the structure. So it's designed to really simplify, right, all of these things. Now, of course, there is the operator minus minus still, but you just have to keep in mind that minus minus means relative to whatever direction you're trying to iterate in, you're going to go in the opposite direction, right? So, meaning if you're starting at the reverse end with a function like rbegin, plus plus is going to take you in the left direction towards the front, right? Minus minus would still be taking you back towards where you started, which was the last element. Or conversely, if you're iterating in the forward direction from left to right, plus plus is going to take you from left to right towards the last element. Minus minus is going to take you backwards, back closer to where you started, which was the first element. So in that sense, the whole idea is that we can use plus plus in both directions, right? As far as advancing the iterator. Because relative to that direction, wherever you did start, whichever end you started at, when you use plus plus, you're moving closer to the opposite end, right? If you use minus minus, you're moving backwards to where you first started in either direction. So that's also important to keep in mind as well. So we want to be careful about that because that's how we need to think about things like plus, plus, and minus, minus, right? So regardless of which direction we're going in, the whole idea is that plus, plus, each time you do it, you're getting further away from where you started, whichever end that was, and you're getting closer to the opposite end. Minus, minus, right? It's the exact opposite way or the other way around, right? Minus, minus, every time you do it, you're getting closer, you're moving closer back to where you originally started, and thus further away from the opposite end of the structure. Um, so the examples we'll see for that reason are going to be using plus plus, right, rather than minus minus, because again, minus minus is just going to be taking you back to the end that you started in to begin with. Plus plus is going to be advancing you closer and closer to the opposite end of the structure, in both the two directions. So we'll see examples of using operator plus plus to properly move throughout that structure. Now, in a general, because some of these structures are also random access, there are also things like plus equal, for example, and minus equal, but those cannot be used right with all the container classes. Because see, the plus plus, for example, moves up one at a time, which you can do that really with any of them. But something like plus equal, right? Similar to, if you have a pointer to a built-in array, you might do PTR plus equals 5 or something, or star PTR, star parentheses PTR plus I to go to some random location, right? But that only works, right, if the elements of the underlying structure are stored together in memory. So things like plus equal and minus equal can be used with the ones that are based on an array, meaning array, DQ, and vector, but not things like list or forward list. So in some cases, we have things that can be used with some types and some that can't be used with others. Because also when you think about those common functions like pushing or popping from one end or the other of the structure, meaning the four functions push back, push front, pop back. Um, some of those can be used with some and some can be used with others. But for example, the array class can't use any of those, right? Because you cannot dynamically change a static array object. Now vector. Well, vector class can use two of them, the ones that work from the back end. Not because it's physically impossible to insert a new element into the beginning, but because it's really not a good idea to be doing that, right, a lot. So the vector class simply does not have a push front or pop front function within that class. That's why it doesn't have those. Now DQ, which is the third random access type structure, does have all four because it works a little bit differently also than vector. So DQ has all four functions. The list class also has all four. Meaning doubly, right? Doubly like this. And then, but forward list only has the front functions, so push front and pop front. So the idea in particular with the way that the forward list class works is whenever you insert a new element, that new element is the new front or the new head of the list, right? So think of it as, insert a node, that node's the head, right? And then another node is inserted, that becomes, the new head or the new front, because that's the way the forward class container class works. So it only has, for that reason, only has the two that work from the front. So there are some cases where a class does not have one or more of these functions, right? Because in particular, vector only has the back functions, right? Forward list only has the front functions. Array can't use any of them. And then DQ and list can use all four of them. So that kind of summarizes the breakdown of the four functions and which ones can be used where. Okay, but we'll go ahead and take our break here and then we'll come back and talk some more about this and also look at some code example. So any questions here before we go to break?